Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Dear student, Assalamu alaikum. I am Dr. Muslim Khan, Assistant Professor, Department of Chemistry, KUST. Today, the topic of our presentation is rate theory of chromatography. Before this rate theory, we have discussed the plate theory in detail, also some aspect of the rate theory, but today we will more focus on the mathematical aspect of rate theory of chromatography. The course code is CHEM455, chromatographic and electrophoretic method of analysis. Let's discuss the rate theory. Scientists want to separate the maximum number of component with ease with the very minimum time possible. Is you know that you have to save the time for analysis as well. Or in other words, increasing the efficiency of the column. In scientific words, all this thing when you say maximum separation and minimum time possible is basically the efficiency of the column. So measure of column efficiency is given by the number of theoretical plates and height equivalent to theoretical plates, HATP. This is explained by plate and rate theory. This plate theory, we have discussed this in detail. Plate theory assumes that the column is mathematically equivalent to a plate, and this column is made of a number of plates. So first, at each plate, each plate you consider it a column. Equilibrium is basically established for at each plate for the solute between mobile phase and stationary phase on each plate. This is very useful theory and it can predict many aspects of chromatographic performance and we have discussed it in detail. The next one is rate theory. Here I have written only the equations, so you have to concentrate on the theory as well. This theory is more scientific and empirical and is more mathematical in comparison to plate theory. So this theory explains the effect of different factors on the separation procedure. According to this theory, separation is due to the stepwise rate of migration. Suppose that the length of the chromatographic column is L, this L, and the time taken by particle on the column is TR, and it is also called retention time. Thus, the rate of migration of retained component is rate of migration of solute retained component is equal to L divided by TR. This is equation number first. So, when sample solution is added to the top of the column, then there are some solute component that come out with solvent without spending any time so taken. Thus, the rate of migration of unretained component is equal to L divided by Tm. So, where Tm is the time taken by the unretained component or time taken by the solvent to come out of the column. This is also called the void time or void volume. There is another factor, this RF, called retardation factor or retention factor, and this is given as RF is equal to, this RF is equal to rate of migration of solute ratio divided by rate of migration of solvent, or RF is equal to rate of migration of solute is given by equation 1, and this is equation rate of migration of solvent is by or by the unretained component is represented by equation 2. Putting equation 1 and 2 in this equation and this RF. So L divided by TR, this one divided by L divided by TM. So cancelling this L and L, we are getting RF is equal to TM divided by TR. Make this equation number third. This is equation number third. This equation represent that if the rate of migration for solute particle in required time, this can also be represented or explained in another way. So this equation represent the rate of migration of solute with respect to the solvent. So the equation number 4, VR is equal to this TR and F multiplied by F. This is equation 4, where VR is called the retention volume and represent the volume of the mobile phase required to elute a retained component from the column. TR is the retention time and F is the flow rate of your mobile phase. So rearranging this equation number 4, we get TR is equal to, this TR is equal to VR divided by F. So bringing this onto the left side of the equation, this become equation number 5. So similarly, this is this TR, time taken by the retained component, is represented by equation number 5. The similarly, time taken by the mobile phase or unretained component of, of your mixture. This is given by equation number 6. Tm is equal to Vm divided by F, similarly like this equation. So Tm is the time taken by the solvent and Vm is the solvent required to elute an unretained component from the column. It is called void volume or dead volume. Putting the value of equation number 5 and 6, this is like this is equation number 5 and this is equation number 6. So here Tm, this is Tm and this is Tr. Putting these two equation and this equation number 3rd. So Rf is equal to Vm divided by F divided by VR divided by F. So FF cancelling each other, RF is equal to Vm divided by VR. This equation is a very important equation. This shows the rate of migration of solute particle and the required volume. This can also be explained in terms of another factor like RF. This RF is equal to Cm minus Vm. It is RF, the flow rate of moving component, where Cm is the concentration of the component in the mobile phase and Vm is the volume of the mobile phase that contains the concentration. Equation number make it equation numbers. Make this is equation number 1. This is this one. 1 minus RF is equal to CS minus VS. So here 1 minus RF is the time in which the solute component is present in the stationary phase. Dividing this equation 1 RF by equation number 2, RF divided by 1 minus RF is equal to Cm minus Vm, Cs minus Vs. And we also know the capacity factor or partition coefficient is given as K is equal to Cs divided by Cm, or 1 by K is equal to reversing this Cm divided by Cs. Putting the value of 1 by K, Cm divided by Cs here, Cm Cs. So this equation becomes Rf divided by 1 minus Rf is equal to Vm divided by Vs multiplied by Cm and Cs is equal to 1 by K. Rearranging this equation, we are getting Rf is equal to Vm divided by Vsk plus Vm. We are getting this final equation. This is another equation for rate theory for we can calculate RF and 1 minus RF and rate theory. So this was more about the rate theory. Column efficiency by rate theory is explained that efficiency of chromatographic column is the measurement of the ability of the column to separate the component of a mixture. Our column efficiency displayed the rate at which the solute traveled through the column or paper. According to the rate theory, the column efficiency is given by H divided by sigma star divided by L. L is the maximum distance traveled by the component throughout the column, and H represents the height of the column, and sigma is representing the standard deviation in the unit height of the column. When sigma is the smaller, the peak is sharp and the column is more efficient. According to the plate theory, the column efficiency is related with the number of plates and is given as we have also discussed, N is equal to L divided by H. So L is equal to NH. Putting the equation there, we have discussed this. So finally we get N number of plates is equal to sigma star divided by H star. So thus two theories are combined in this equation. This shows that smaller the size of the plates, greater will be the number and more efficient will be the car. The next is we are getting basically a band broadening or zone broadening. Like in this example, we have material with the same elution time but different number of plates. So zone broadening is related to the actually the mass transferring processes. First of all, this band broadening is a major problem because it affects the resolution of solute that have similar retention time. The peak width increases with the square root of column length. Therefore, we just can't make a column longer to obtain a better separation. Like these are the example. Here, very sharp peak, little bit broad. For this component, a very broad profile. So this is known as a band broadening. So basically rate theories explain these band broadening. So plate theory neglects the concept of solute diffusion through the column and flow paths which lead to the band broadening. Rate theory accounts for these and presumes band broadening is caused due to the number one, slow equilibrium of solute between mobile and stationary phases. And the second is time is required for the solute molecule to diffuse from the of interior of this phase to their interface where transfer occurs. So theory of broad broadening is basically explained by this one diameter equation. Theoretical study of zone broadening in 1950s by a Dutch chemical engineer lead to the one dimensional equation, which can be written as H is equal to B Cs mu plus Cm mu, where B is the longitudinal diffusion, we will discuss. Cs is the mass transfer coefficient in the mobile phase, and Cs is Cm. Cm is the mass transfer coefficient in the stationary phase. Mu is the velocity of the mobile phase. So first of all, this longitudinal diffusion. This longitudinal diffusion is term B divided B mu depends upon dm diffusion coefficient. Solute continuously diffuses away from the concentrated center of its zone. In the column, there are diffusion towards the different sides of the column due to the random motion of the particle. Diffusion towards sides and upward in the column. This also leads to the peak band broadening. The longitudinal diffusion can be minimized. The upward diffusion in the mobile phase can be eliminated by increasing the pressure of the flow rate of the mobile phase down the column. So this zone of salute after a short time on the column, a zone of salute after long time on the column direction of the travel. So the longer the salute in the column, broadening effect increases. The next one is mass transfer effect. In case when the stationary phase is solid, then it contains small pores. These are filled with mobile phase, which does not move, means stagnant. A sample molecule entering the pore is stopped by this stagnant mobile phase, and sample molecules only changes its position or move down the column by diffusion. This movement take time and cause the band broadening. Similarly, when sample is injected, then it is confronted with a fresh carrier gas mobile phase which pushes it towards the column. At this stage, there is no equilibration between the stationary phase and the mobile phase, and the mass is transferred to the column where it is absorbed, stuck, and don't move for a while. The desorption transfer of mass back to the mobile phase take place. So this alpha is the thickness of the stationary film on the support particle. This is alpha, the flow rate, 1 by alpha diffusion coefficient of the solute in the film. Slower rate of mass transfer increases plate height, which is undesirable. So mobile phase, stationary phase, direction of elution is like this. So there are pores in the plates in which this mobile phase is stuck there, and this is then band broadening is occur because of this stagnant mobile phase. So this mass transfer we have discussed. So zone broadening or band broadening occur due to the AD diffusion, different path length passed by the solute, and diffusion of solute from one stream of mobile phase to another, stagnant or static pools. The third one is AD diffusion. So AD diffusion, it is the process in which the molecule migrate from the region of higher concentration to the region of lower concentration. The contribution of diffusion towards the chromatographic separation is not much significant. It is the fast flowing, this AD diffusion. It is the fast, so AD diffusion is the phenomena of migration due to the multitude, many pathways through which the solute particles elute along with mobile phase. The length of these pathways through the column is different. So the residence time of the solute on the column for the different pathways are the different. So the same species are also different, and in this case, some particles are eluted first and some are eluted little bit with a longer pathway. So that's why peak broadening is occur. So this is also one of the factor responsible for the peak broadening during this chromatographic run. So zone broadening or peak broadening occurs mainly due to the number one, AD diffusion, number second, this mass transfer effect, and third one is because of this diffusion of solute from one steam mobile phase to another phase. This is like AD diffusion is given in this example. For example, this is path number one, in which solute is going through this path, this. This is path number two. Solute is along with solvent is going through this path, this. This is a bit longer pathway. So these, when those solute particle of your component are coming through this one, this will be eluting later because this is covering a very larger distance. So, and this one, the third one, this is a more longer pathway through this. So, AT diffusion. Similarly, when you are, this is a mobile example of mobile phase mass transfer, and this is the stagnant mobile. These are the pores in which here this is stagnant mobile phase mass transfer, in which some of the mobile phase is stagnant here in the here. So these are the factors responsible for the mass transfer effect. So we will discuss some more aspect of the chromatographic, and at the moment, please follow these two books, G.T. Christ in Analytical Chemistry, 7th edition, and Scooge and West, 9th edition. Thank you very much.